Hello everyone. In today's lecture, to express the noise quality of the receiver, we will study the following terms: signal to noise ratio, noise figure, noise temperature, and at the end of the lecture, we will solve some problems related to the noise. Now, let us see what is the signal to noise ratio. In communication, noise is usually expressed as a power because the received signal is also expressed in terms of power. So, if the signal and noise powers are known, then S by N ratio can be calculated. So, the S by N ratio can be calculated in terms of decibel dB equal to 10 into to the log to the base 10 of signal power to the noise power. This can also calculated in form of the signal voltage and noise voltage. So it is like this. If you take the S by N ratio equal to the electrical power, signal power can be write as the signal voltage divided by the resistance R and the noise voltage square divided by the resistance R. So it becomes Vs by Vn square. Means this SNR can be calculated by taking the square of the ratio of the signal voltage to the noise voltage. This S by N ratio is usually expressed in terms of decibel. So let us one example to calculate the S by N ratio in dB. Now if there is the input signal power is 1.5 microwatt, let P signal is equal to 1.5 microwatt, and the noise power, that is generated by the P noise, and that is equal to 0.2 microwatt. Now if we substitute this in above formula, it will be 10 log of 1.5 to 0.2. So the value is 3 near to 3 dB. So in this way, the SNR can be calculated if you know the signal power and the noise power. Now let us erase this. Okay. Now the next term required to calculate or to know the sensitivity of the receiver, that is noise figure. This noise figure describes the performance of a device. Since for a receiver the channel is the input, to express quality of the receiver more properly, the noise quality of the receiver noise figure is used. So what is noise figure? The noise figure is the ratio of S by N power at the input to the S by N power at the output. So it is written as like this: F is equal to S by N at the input divided by S by N at the output. It can express in terms of dB by taking 10 into log of this F, that will be in terms of dB. The input and output may be for entire receiver or a single amplifier stage. The noise figure F is also called as a noise factor. The noise figure is a number, usually it is also expressed in terms of decibel. So as already told, AM amplifier or receiver will always have some noise at output than at the input. So this is to the fact that the amplifier or receiver generates internal noise, and along with the signal, noise also get amplified. The SNR at the output will be less than the SNR at the input, and therefore the noise figure always greater than 1. The ideal receiver contributes the zero noise to the signal. So the ideal receiver have the noise figure is equal to 1 or 0 dB. But such a noise figure cannot be obtained in practice. The lower the noise figure, better is the amplifier or receiver. Now, the third term, which is the noise temperature, and this noise temperature also used to express the quality of the signal. The noise figure is used to express noise in the receiver. It is not very convenient, especially dealing with the ultra high frequencies and microwave low noise antennas, receivers, or devices. Another method of expressing the noise in an amplifier or receiver is to use the noise temperature. Most of the noise produced in a device is thermal noise, and that is proportional to the temperature. The noise temperature is expressed in terms of Kelvin given by using this formula. T of n is equal to 290 into F minus 1. An amplifier or receiver contributes no noise, then the noise factor F is equal to 1. Start with the solving the problems. So the first problem is based on bandwidth. So before solving the problem, let me correct in the problem. The voice frequency ranges from 300 Hz to 3000 only Hertz. It is not kilohertz. So just remove the K. So now the problem is calculate the bandwidth required for transmission of voice frequency ranges from 300 Hz to 3000 Hz. How to solve this problem? As you know that the bandwidth is calculated by using the formula F2 minus F1. Means F2 is the higher frequency and F1 is the lower frequency of this range. And here in voice frequency, higher frequency in the range is 3000 Hertz minus 300 Hertz. So it is just subtraction of these two figures. It becomes 2700 Hertz. So this is the bandwidth is required for transmission of these voice frequencies. Now let us solve the second problem. As in the second problem, to calculate the signal to noise ratio in dB, as you know, the signal to noise ratio is expressed in dB 10 log of P signal to the P noise. So here these two values are provided, that is a signal power is 1.5 and noise power is 0.7 microwatt. divided by 0.7 microwatt. So after solving this, it will be 3.3 dB. Okay, this is just substitution and solve it. The answer is 3.3 dB. Okay, the next problem is based on noise temperature, that equivalent noise temperature that can be calculated as the formula, using the formula T of N, that is the equivalent noise temperature, equal to 290 F minus 1. So this is straightforward problem. Just substitute the value of F, that is the noise peak factor, is provided. F is the noise factor and that value is given in problem. So you just substitute the value, 290 into 1.5 minus 1. So this becomes 290 into the 0.5. If you multiply by 290 into 0.5, it is 145 degree Kelvin. Next problem, which is to calculate the noise voltage if the resistance value is given and room temperature is given and the bandwidth is for 100 kilohertz. So how to solve this problem? As you know, the thermal noise voltage noise voltage equal to V square of this, Vn square equal to 4 R K T into B, where R is the resistance value which is provided in the, which is given in the problem. K is the Boltzmann constant, room temperature is the T, and B is the bandwidth. Substitute these values and calculate it. So after calculation, this value of the noise voltage becomes 5.66 microvolt. So here also no conversion, straightforward problem is this. Just substitute the values and find with the proper calculations, find the value of noise voltage. Okay, now let us see the another problem. Two resistors of values 10 kilo ohm and 20 kilo ohm are in series at a room temperature 290 degree Kelvin. Calculate the thermal noise voltage for a bandwidth of 100 kilohertz. This problem is same as earlier one, only here the resistance values are provided. Two resistors values are given and that are in series. So therefore the total resistance here is 10 plus 20 kilo ohm, and that is the 30 kilo ohm. So the formula to calculate the thermal noise voltage is Vn square is equal to 4 R K T and B. Here R will be 30 kilo ohm, K is the Boltzmann constant, that value is 1.38 into 10 to the power minus 23 joule per Kelvin. So substitute all these values and you will find this noise voltage is 6.93 microvolt.